Hello there, and welcome to Sleepy Cosmic Podcast, where we wander beneath velvet skies, following ancient light on its unhurried path through time. Tonight, above your quiet room, the sky stretches beyond what the eye can see. Stars blink in soft silence, and somewhere between them, something once moved across that darkness, something strange and silent, a whisper in motion that changed how we see our place in the cosmos. You might remember the headlines in 2017. A visitor had arrived, not from another planet or even from the far edges of our solar system. This one came from interstellar space, a place between the stars. It was named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, and in many ways it truly was the first. If this kind of quiet wonder helps you rest, I'd be grateful if you tap like or subscribe. No pressure at all. Wherever you're listening from, your bed, your couch, your favourite chair, I hope it's peaceful. Maybe it's late at night or early in the morning. Maybe the hum of a fan keeps you company, or the sound of distant city lights fades into your background. Now dim the lights, maybe turn on a fan for a soft background hum, and let's ease into tonight's journey together. Oumuamua entered our solar system quietly. It wasn't seen until it was already on its way out. A small, fast-moving object with a steep hyperbolic path, meaning its trajectory wasn't looping like planets or comets bound to the sun. No, this one had come from far beyond, passed close by, and was never coming back. Astronomers first spotted it using the Pan-STARRS telescope in Hawaii. At first, it was thought to be just another asteroid. After all, we see thousands of those, but as they tracked it and ran the numbers, something felt off. The speed, the angle, the way it moved. It was the first object we'd ever confirmed to be from another star system. Its path was so steep that it must have been drifting between stars for millions, perhaps billions, of years before we caught a glimpse. And even then, we only saw it because we happened to be looking in just the right direction, at just the right time. If Pan-STARRS had been focused elsewhere, it would have passed without a trace, just another silent shadow brushing past our sun. Oumuamua's speed told us that it wasn't native to our solar system. At its fastest, it was moving at over 87 kilometers per second, far faster than anything orbiting within the sun's gravitational embrace. The way it curved around the sun, then shot back out, was a gentle arc, not a loop, a visitor, not a resident. And yet, even as we tracked it, the mystery deepened. It didn't look like what we expected. Comets tend to sprout tails when they get close to the sun, jets of gas and dust, glowing softly as their frozen surfaces warm. But Oumuamua had no tail, no glow, just a faint dot that seemed to dim and brighten in strange uneven rhythms. Some astronomers compared it to a tumbling sliver, a long, thin shape spinning erratically, like a shard of something broken or a flake of metal, but it was too far and too faint to resolve clearly. We never got a photo that showed its shape, only dots of light, measurements of brightness, hints from the way its signal flickered, and then, just as quickly as it arrived, it was gone, sliding away from the sun, fading into the outer darkness, disappearing faster than we could understand it. We tried to point every telescope we had, but it was too fast, too small, and too far. Still, what it left behind wasn't a wake of light or debris, but a trail of questions. Was it a piece of rock? A frozen splinter? A shard of a world torn apart? Some even wondered aloud. Was it something artificial? A probe, perhaps? A light sail from a long-forgotten civilization? Theories came and went, each one trying to explain its shape, its motion, and its quiet refusal to glow like a comet should. But in the beginning, all we knew was this. Something ancient and foreign had passed us by. A traveller from beyond the stars brushing past Earth as if we were just another planet in a long-forgotten map. We caught a glimpse, wrote down its name, and watched it fade. To this day, we still don't know exactly what Oumuamua was. It didn't give us enough time. It came too fast, too faint, too early in our era of skywatching, and perhaps that's part of the reason it has held our attention so tightly ever since. Sometimes the most powerful mysteries are the ones that whisper as they pass, that don't stop to explain themselves, that arrive without warning and leave before we're ready to ask the right questions. And so, Oumuamua became more than a rock. It became a symbol, a quiet echo of something larger, a hint that we are not alone in the void, not in the sense of life necessarily, but in the sense of movement. That space itself is not still, that stars, planets, rocks, and maybe stranger things drift through the night, slipping from one system to the next over spans of time so vast they almost lose meaning. And we happen to look up just once and see one go by. When we saw Oumuamua flickering through our telescopes, it wasn't just the path that surprised us. It was the way it danced, a strange rhythm of light and shadow that hinted at something unusual in its shape. Unlike the softly rounded asteroids or the loosely clustered comets we'd catalogued for decades, this object had a light curve unlike anything we had tracked before. As it tumbled through space, the brightness we measured from Earth changed dramatically. It didn't pulse steadily. It flickered and faded in irregular cycles, suggesting an elongated form, not a sphere or even a lumpy potato-shaped rock, but something much longer than it was wide, perhaps 10 times longer according to some estimates. We imagined a thin shard spinning end over end, flashing one side toward us, then the other, then vanishing into darkness before tilting again. The object didn't reflect light evenly, and that uneven glint told us it wasn't smooth or regular. It might have been flattened, like a cosmic pancake, or a needle drifting through space. Astronomers leaned into models, trying to recreate its flicker, its change in brightness, its slow and chaotic spin. The results hinted at a cigar shape, perhaps even thinner. Maybe it was a sliver, a flake, a fragment. Whatever it was, it didn't resemble the rounded, tumbled rocks we expect from our own solar system's birth. But even that, strange as it was, wasn't the most peculiar part. Oumuamua didn't behave like a simple rock. As it curved away from the sun, it sped up slightly. Not much, just enough that our models of gravity alone couldn't quite explain it. There was a slight acceleration, subtle but measurable. That's where the real mystery began. Typically, when comets accelerate like this, it's because they're outgassing. Sunlight warms their icy surfaces, causing vapour to jet out from one side like a faint engine, pushing them slightly. It's gentle, and it happens often. But Oumuamua showed no signs of a comet tail. No visible gas, no glow, no detectable emissions. So the acceleration was there, but not the reason for it. Some scientists proposed that maybe it was outgassing, just too subtly for us to detect. Maybe the jets were composed of molecules that don't reflect light well. Others suggested something more speculative, that the object's shape and reflective surface allowed it to be nudged slightly by sunlight itself. This idea, known as radiation pressure, works much like a sail catching a breeze. If Oumuamua were thin enough, like a giant sheet of foil drifting through space, then the faint pressure of sunlight might be enough to give it a gentle push. It was around this time that conversations turned toward even stranger possibilities. Could it be artificial? A discarded probe? A fragment of some long-lost civilization? A broken piece of alien technology still drifting between stars? For most astronomers, these were curiosities, not conclusions. But for a few, they were questions worth asking seriously. Because in science, even unlikely ideas deserve a glance, if the data can't yet rule them out. But there was one problem we couldn't escape. Whatever Oumuamua was, it was already gone. By the time the world realized how strange it was, it had faded from view. No new data would come, no probe could chase it. We had missed our chance. And so, the questions lingered in the dark, like echoes in a cave, like a whisper you're not sure you heard. Still, there were things we could say for sure. We knew its speed. We knew its trajectory. We knew it had come from far outside our solar system and it wasn't coming back. We knew it had passed close, just 24 million kilometers from Earth at its nearest point, about 60 times the distance to the Moon. Close enough that a well-timed mission could have reached it, if only we'd known to prepare. We knew that it was small, somewhere between 100 and 300 meters long, not a spacecraft, not a mountain, just a tumbling shard smaller than many city blocks, and we knew that it had no analogue. No known comet or asteroid quite fit the same pattern. It wasn't icy like the comets that streak across our skies. It wasn't rocky like the near-Earth asteroids we monitor. It was other. Some tried to name it a comet, despite the lack of a tail. Others insisted it was an asteroid, albeit a strange one. The International Astronomical Union finally settled on a new label, interstellar object, and they gave it a designation, Oumuamua. The one I stood for first interstellar, but we wondered how many more might be out there. Was this truly the first, or just the first we noticed? Our telescopes had never been great at spotting fast-moving objects, especially ones coming in from unexpected angles, moving too fast to track easily, fading into the stars before we could point again. What if the solar system had been brushed by visitors like Oumuamua many times before? Quiet, unseen, slipping in and out under our notice. There was something humbling in the idea that the vastness around us may be more crowded than we thought. Not with ships or cities, but with fragments and flotsam, pieces of long-gone worlds, wandering like dandelion seeds through interstellar space. Oumuamua reminded us how little we still know about our cosmic neighbourhood, about what drifts between the stars, about the stories hidden in motion too quiet to catch. But that wouldn't be the last whisper we heard. After Oumuamua vanished into the darkness, astronomers were left with a kind of restless quiet. They had tracked something extraordinary, but with no way to follow, no way to observe again, and no data left to collect, the window had closed. The questions remained, circling in scholarly journals and late-night telescope logs. What was it? Where did it come from? And perhaps most importantly, was it truly unique? For a while, we had no answer. But curiosity doesn't fade so easily. Around the world, new sky surveys were coming online. Projects like Pan-STARRS, which had discovered Oumuamua, continued their work. Other observatories, like the Atlas system, short for Asteroid Terrestrial Impact Last Alert System, joined the watch. Atlas was designed to catch near-Earth objects, scanning the skies nightly for anything moving in ways that suggested a potential impact. But its wide-field approach also made it particularly good at spotting anything unusual, including fast visitors from beyond. As more data poured in, astronomers began to model how often interstellar objects like Oumuamua might drift through our solar system. The estimates were surprising. Based on that single detection, some models suggested that thousands of such objects might pass through each year, most too small or too faint to notice. In essence, Oumuamua may have been the first we saw, but not the first to visit, just the first whose shadow we managed to catch. This realization brought a quiet shift in perspective. Perhaps interstellar visitors weren't rare at all. Perhaps we'd simply lack the tools, the reach, and the watchfulness to see them. And then, in 2024, something happened that reawakened all those questions. Another object appeared. A new interstellar traveller entering from the darkness with its own quiet story. This one was labelled 3 Atlas. The 3I meant it was the third confirmed interstellar object, after Oumuamua and 2I Borisov, a comet-like visitor seen in 2019. But unlike either of those, 3I Atlas seemed to arrive at a perfect time. Our telescopes were better, our systems more alert. We didn't miss it. This new traveller entered slower than Oumuamua. It was brighter, It stayed longer, and from the very beginning, it gave us a chance Oumuamua never had, a chance to watch closely. We could observe it from multiple angles. We could track its spin, its brightness, its shape, its motion. We could point powerful instruments toward it and begin asking the same old questions, only now, with more tools and time to find real answers. This was the beginning of a new kind of observation, a slow, careful look at a messenger from the deep. As 3 Atlas glided into view, astronomers began tracking its movement with precision. Its trajectory was hyperbolic, just like Oumuamua's, a clear sign that it was not bound to the sun. It had come from somewhere else, passing through briefly, and then it would go. But even from those first calculations, it was clear that this object was not simply a repeat of Oumuamua. The angle of its entry was different. The brightness changed more gently. It appeared larger, more massive, easier to track. There was no ambiguity this time. It wasn't a blurry flicker on a few frames. It was a real, persistent signal, something we could follow for months, and that meant we could begin asking deeper questions. Was it icy? Did it outgaze like a comet? Was its path affected by solar radiation, like Oumuamua's might have been? Did it spin? Was it a tumbling shard or a rounded body? The early signs were promising. 3I Atlas showed signs of outgassing, those faint jets of vapour that mark a true comet. It had a visible coma, the hazy cloud that forms when sunlight heats surface ice and turns it to gas. Already this made it different from Oumuamua. Where that first visitor had kept its secrets, 3 Atlas seemed more willing to speak. But the story wasn't simple. As more data came in, scientists noticed irregularities, oddities in the composition, strange shifts in brightness. Its chemistry didn't quite match comets from our own solar system. It had hints of carbon monoxide, perhaps even more complex molecules, things we didn't expect in such high concentrations. And so, the debate resumed. Was this a typical interstellar comet, or something else entirely? Even among astronomers, the answer wasn't unanimous. Some saw in 3I Atlas a natural object, formed in the outskirts of a distant solar system, ejected in a collision or a gravitational dance, and sent adrift across the galaxy. Others noted the strangeness, the speed, the shape, the unusual light curve, and wondered aloud if we were again brushing against something more exotic. Perhaps not artificial, but not quite familiar either. More instruments were brought to bear. Radio telescopes scanned for signals, just in case. Spectrometers measured light at every wavelength. Orbit models were refined. Predictions were made for how long it would stay visible. This time, we wouldn't let it slip away unnoticed. For months, 3I Atlas remained in view, gliding across the sky like a soft punctuation mark in the sentence of the stars. And just like Oumuamua before it, this new visitor whispered of something larger, that the galaxy is not still, that there is motion in the void, that even the space between stars carries echoes of distant worlds. Now Atlas was not just another rock, it was a reminder that we live not in isolation, but in a cosmos where even silence moves. The moment we realised that 3I Atlas wasn't just another passing blur, we began to compare. Side by side in our models and memories stood 2 interstellar visitors, Oumuamua and 3I Atlas. Both had entered from the dark. Both had curved around the sun, then drifted away. Both had arrived uninvited, carrying with them a hush of wonder and a list of unanswered questions. But the differences were just as telling as the similarities. Oumuamua was fast, unusually so, zipping into the solar system at a speed that suggested a long journey through galactic space. It moved erratically, with a faint push that some believed came from sunlight itself. Yet it never glowed. No outgassing, no visible tail, just silence and flicker. 3. Atlas, by contrast, moved more slowly. Not slow in human terms, of course. It still travelled tens of kilometres per second, but by celestial standards it was more measured. This gave us time to observe, time to react, time to wonder aloud, and then look again. And unlike Oumuamua, 3i Atlas did glow. From the moment it began to warm under the sun's rays, astronomers noted a faint coma, a ghostly halo of vapour and dust much like the comets we know. It left behind a wispy tail, a signal of activity. This suggested it was icy, volatile rich, and more like the frozen bodies in our own solar system's outer edges. This mattered. It meant we could learn more from it. If Oumuamua had left us with half a puzzle, 3i Atlas brought at least a few more pieces. Its behaviour gave us a baseline, a way to test our expectations. If most interstellar objects were like this, small, icy, active, then perhaps Oumuamua had simply been an outlier. Or perhaps Oumuamua had been the norm, and 3i Atlas was the anomaly. It's still too early to know for sure. Astrophysicists continue to model how objects are ejected from distant star systems. There are many ways a piece of ice or rock might be flung into space: a near collision with a giant planet, a gravitational shove from a binary star, the quiet chaos of a forming system where debris slingshots outward, never to return. And depending on where these fragments come from, their size, shape, and composition could vary dramatically. Some may be rocky, some icy, some dust-covered, others stripped bare by long exposure to cosmic radiation. It's possible that Oumuamua and 3i Atlas are both normal, just born of different kinds of worlds. One may have come from a place where surface ice had long since vanished. The other from a gentler origin. Its ice is preserved by colder, quieter light, and so we turn to their paths through the solar system, their angles of entry, their slight curvatures and acceleration. Oumuamua's trajectory had been steep and fast, entering from above the plane of the solar system, not along the gentle ecliptic where most planets reside. It was a swift diagonal, like a falling leaf caught in a crosswind. 3i Atlas too entered from a non-ecliptic angle, but its path was less dramatic, more gradual. This made it easier to track, easier to photograph, easier to study in depth. Where Oumuamua had blinked past us like a skipped heartbeat, 3i Atlas moved like a sigh, still fleeting but slow enough to notice. Even the way they spun told us something. Oumuamua's brightness changed rapidly and erratically, hinting at a tumbling motion, not just spinning but chaotically rotating on more than one axis. This kind of motion is difficult to model and harder still to explain for something shaped like a needle or flake. 3D Atlas showed a more stable spin, less dramatic, less chaotic. Its light curve was smoother, easier to fit into predictions, not perfectly regular, but familiar. And this familiarity, quiet as it was, helped us breathe a little easier. Oumuamua had startled us, not just by its arrival, but by its refusal to conform. It was, in many ways, the cosmic equivalent of a footprint with no matching shoe. 3i Atlas felt more like a comet we could understand, but that didn't mean it was ordinary. Its spectrum, light broken into wavelengths to reveal composition, suggested materials not commonly seen in our neighbourhood. A stronger presence of carbon monoxide, for instance. An absence of certain organic compounds. Hints of molecules that might form only in colder, more distant places. Its brightness curve hinted at a smooth surface, or at least one with few large outcrops. That might mean it hadn't been battered by collisions the way so many solar system objects have. Perhaps it had drifted alone for eons, untouched since its ejection. And that raised another possibility. Maybe this object was older than anything we'd ever studied up close. Maybe it had been wandering between stars since before Earth's oceans formed. Maybe it had seen the birth of stars that now only exist as whispers of light. Maybe it carried the chemistry of worlds long gone, or never finished. We could only guess. But the contrast between these two visitors reminded us of something fundamental. We are still at the very beginning of interstellar study. 2 data points, wildly different, are not enough to define a pattern, but they are enough to open the door. With Oumuamua, we learned how easy it is to miss something extraordinary. With 3i Atlas, we learned how important it is to be ready. As the stars drift slowly across the sky and telescopes scan the darkness, we now wait with a different kind of awareness, not hoping perhaps, but prepared for the next shadow, the next flicker, the next visitor from beyond, because now we know they're out there. When Oumuamua faded from view, it left behind more than mystery. It left behind a silence, a gap we couldn't fill, no matter how many papers were published or models were drawn. We had caught a glimpse of something rare, something ancient, and then watched helplessly as it slipped beyond our reach. There was no second pass, no do-over, just the long hush of unanswered questions. In that quiet, something interesting happened. Our instruments got better, our surveys grew wider, and perhaps most importantly, our attention sharpened. Astronomers began to refine how we look at the sky, not just for objects that stay, but for those that pass through. 3 Atlas arrived into that improved landscape, and with it came a different kind of silence, not one of the absence, but of stillness. A quiet signal that didn't vanish too soon, a whisper we could actually follow. Even as we studied its movement and measured its chemical traces, there was something poetic about its presence. Interstellar objects don't circle back. They don't belong to us. They appear, curve softly around the sun, and continue on their way, like letters meant for someone else, briefly intercepted mid-journey. And yet, in their brief passages, they say so much. 3 Atlas didn't shout. It didn't flare or explode. It didn't leave behind a trail of dust thick enough to study from the ground. But what it did offer was time. Time to think. Time to recalibrate our expectations. Time to understand that the silence between stars is not empty, but full of slow, drifting stories. As it continued its arc away from the sun, we kept watching. Telescopes followed its retreat. Spectrometers measured every shift in light, and still there was no clear origin point. Its incoming vector placed it somewhere between constellations. No obvious star, no known system it might have come from. This is not unusual. By the time an interstellar object reaches us, it has likely been travelling for millions of years, its path bent by gravity, its speed nudged by close passes with stars or unseen masses. Pinpointing an origin is like trying to find the mountain that birthed a single flake of snow carried by wind across continents. But the shape of that path still tells us something. The trajectory of 3i Atlas, like Oumuamua before it, was hyperbolic, a curve too wide to form a loop, not bound by our sun's pull. Its motion told us it came from the outside, not from the cold, quiet zones beyond Neptune, where long-period comets sometimes begin their fall. No, this was not one of ours, and that made its silence all the more beautiful, because in the absence of a clear answer, we are left with possibility, and possibility is its own kind of wonder. Some researchers modelled the object's velocity relative to the sun and traced it backward, trying to see if it might have passed near any known stars in the last few million years. A few candidates appeared. None were definitive. The uncertainties were too large, the galaxy too vast, the paths too easily bent. Others turned their attention to the chemistry, wondering if its makeup could hint at a different kind of solar system, a system colder perhaps, or richer in carbon compounds, a place where ice clings longer and sunlight fades faster. And all the while, the object moved on, slipping farther and farther away from the blue warmth of our sun, heading back into the quiet dark. That's the thing about interstellar objects. Their stories are not contained by our system. They are chapters from other books, drifting through our library. We catch a few lines, a phrase or two, and then the pages turn. But even brief encounters leave marks. Astronomers now talk about Oumuamua and Three-Eye Atlas in tandem. Together they form a new kind of data. A quiet pairing that suggests interstellar visitors are not mythical, not rare in the way we once thought, just quiet, just hard to see. And with each one, we learn a little more. We learn how to detect faint tails in low light, how to measure acceleration too subtle for gravity alone, how to read the shape of a light curve and translate it into a whisper about spin or texture or age. More than that, we learn to look up with new eyes, to see the solar system not as a closed bubble, but as a crossroads, a place where objects pass through, where gravity curves and stories intersect, where even the quietest visitor leaves ripples behind. Three-Eye Atlas, like Oumuamua, won't return. Its path is set. Its silence stretches ahead of it like a shadow across stars. But the wake it leaves, soft as it is, shapes the way we see the next traveller, and the next. Because now, we're listening. We're more alert, more curious, more prepared. And as the darkness around Earth deepens each night, and telescopes scan the sky from mountaintops and deserts, and space itself, we know something we didn't know before, that silence is not emptiness, that the void between stars carries secrets, and sometimes they drift close enough to see. The search for these drifting visitors, the ones that come from beyond our solar system, has become a quiet revolution in modern astronomy. Not because they arrive often, or loudly, or with bright fanfare, but because we've finally learned how to watch for them, and that watching has changed everything. To do it properly, we had to widen our view. In the past, we focused our attention where the action was, along the ecliptic, that thin slice of the sky where planets and comets tend to reside. We watched for near-Earth asteroids that might someday pass too close. We tracked the predictable paths of known objects, keeping our gaze tight and focused. But Oumuamua taught us that interstellar visitors don't follow those rules. They come from above or below, from angles that defy our traditional maps. They cross through our solar system like wanderers, not born here, not bound here, just passing through. And so, to catch more of them, we began to look wider. Atlas, short for the Asteroid Terrestrial Impact Last Alert System, was built with that principle in mind. It's designed to scan the entire visible sky multiple times each night, not just the ecliptic, not just known trajectories, everything, and that makes a difference. Atlas uses modest telescopes, but their power lies in coverage. Two main observatories, one in Hawaii and one in South Africa, scan the night sky from opposite hemispheres. They take rapid, wide-field images and compare them with previous frames, looking for anything that moves. When they see movement, especially something moving fast and not on a known orbit, alerts go out. Other observatories swing into motion, larger telescopes zero in, spectrometers begin measuring light, and the quiet dance of discovery begins. That's how Three-Eye Atlas was caught. Its motion betrayed it. Fast enough, steep enough, strange enough to raise eyebrows. Not bound to the sun, on a one-time pass, and within days of its detection it was already under worldwide observation. It might not have happened without Atlas, or without pan-stars before it, or without the lingering mystery of Oumuamua, which reminded us what we could miss if we weren't watching carefully. We now live in an era of wide eyes, sky surveys that don't sleep, networks of telescopes working together, algorithms tuned to see the unusual, and every improvement increases our chances of catching these interstellar passers-by. Soon, a new generation of observatories will make that search even more powerful. The Vera C. Rubin Observatory, for instance, is set to revolutionize sky watching. With its massive mirror and wide-field camera, it will image the entire visible sky every few nights with unprecedented detail. When it comes online, we expect a flood of discoveries, asteroids, transients, strange flashes, and yes, more interstellar visitors. not just once every few years, perhaps once every few months. Some scientists estimate that with these new tools, we may be able to detect dozens of interstellar objects per year. Tiny ones, bright ones, slow ones, strange ones. And as the dataset grows, so too does our understanding. With more examples, we'll begin to see patterns, to understand what's common, what's rare, what types of objects survive long journeys through interstellar space. We'll refine our models, our assumptions, our sense of how other star systems live and die. Every interstellar object carries clues, not just about itself, but about the place it came from, about the processes that ejected it, about the conditions that shaped its surface. Maybe some are leftovers from planet formation. Maybe others are fragments of collisions or ancient moons set adrift. Maybe some carry molecules we've never seen before. Maybe, someday, one will carry something more. But for now, the goal is simple: to watch, to record, to learn, to keep our eyes wide and our minds open, and to remember that space is not a closed room, but a passageway. Even now as we speak, the surveys continue. Cameras click, images upload, algorithms comb through the frames line by line, hunting for the faint traces of motion that might mean another traveller has arrived. Most nights, they find only silence, a quiet sky, full of familiar stars. But every so often, something moves, something strange, something that doesn't quite belong, and in that moment, we begin again. We turn our telescopes, we call our colleagues. We draw orbital maps and watch the arc unfold, and we whisper a small hope that maybe this one will stay just long enough for us to listen. And then came 3I Atlas. Spotted in 2024, its appearance felt like a soft answer to the questions Oumuamua left behind. A second chance, maybe, or a quiet continuation of a conversation started years earlier. Only this time, we were listening with better ears. From the moment 3I Atlas was confirmed as interstellar, it became a kind of scientific meditation. No alarms, no dramatic revelations, just careful observation. An invitation to slow down, to track its motion through our shared sky with patience. Its brightness was steady enough to measure across many nights. Not brilliant, but reliable. We could trace its arc not just in space, but in time. From its first arrival, it lingered for months, an unusually long visit by interstellar standards. Its speed, while still swift, was more manageable. It entered the solar system at around 26 kilometers per second relative to the Sun, far slower than Oumuamua's roughly 87 kilometers per second. And that gave us room to breathe, to watch, to think. One of the earliest revelations came in the form of light, specifically how the brightness of 3I Atlas changed over time. This variation helped us understand its shape and rotation, how it spun, whether it tumbled, and how sunlight bounced from its surface. Unlike the erratic flickers of Oumuamua, which hinted at a chaotic, lopsided body, 3I Atlas displayed a more stable pattern. Its rotation wasn't perfectly smooth, but it was less wild. This suggested a more compact shape, perhaps spherical or slightly elongated, but not the strange shard-like silhouette that haunted models of Oumuamua. We also caught the earliest signs of outgassing, faint but clear. A gentle release of vapour from its surface as solar warmth reached buried ices. It wasn't dramatic, no bright jets, no explosive activity, just a whisper of evaporation, visible only through sensitive instruments. But that whisper told us something profound. 3 Atlas had surface volatiles, frozen gases that sublimated under heat. In other words, it behaved like a comet, a real one. This gave astronomers something they longed for, a direct comparison, an interstellar object that could be studied using familiar models, a visitor that fit within our known categories, yet still came from the great beyond. It also lent weight to a quiet idea that had been gaining traction. that Oumuamua may not have been the rule, but the exception. That perhaps most interstellar objects are more like 3i Atlas, icy, active, familiar. If true, it would shift our expectations entirely. We could start thinking in terms of families, not outliers. We could begin assembling a taxonomy of visitors, icy ones, rocky ones, dormant ones, luminous ones. But first, we needed to listen more closely. Spectral analysis revealed subtle clues about 3i Atlas's composition, hints of carbon monoxide and carbon dioxide, which are common in solar system comets, but in slightly different proportions. Some wavelengths showed absorption bands that didn't quite match any known templates. Perhaps the object had formed in a colder, more distant place. Or perhaps its long journey had altered its surface, bombarded by cosmic rays, micrometeorites, and the relentless weathering of time. Either way, it bore fingerprints of another world. But whose? That remains the open question. The path of 3i Atlas, like Oumuamua, could be traced backward, but only so far. Over millions of years, gravitational nudges blur an object's origin. Its motion today tells only part of its story. And so, the source remains uncertain. Some traced its trajectory and found that it might have passed near the Carina or Vela constellations several million years ago. But without a clear match to a known star system, this remains a soft guess. Still, the speculation invites wonder. Could it have come from a system like ours? A dusty, quiet solar twin with its own icy debris field and wandering comets? Or perhaps from something stranger, a binary star, or even a failed stellar nursery where worlds never fully formed? We may never know. But 3i Atlas brought us closer. It gave us data, light, spectra, motion. It gave us something to hold on to. Not a conclusion, but a path forward. It also served as a reminder of how interstellar objects might survive the ages. For a body to drift for millions of years and still carry surface ice suggests a deeply cold origin, or a gentle path through space. Perhaps it travelled through less active regions of the galaxy. Perhaps its surface shielded the ices within. Perhaps the vacuum preserved it better than we imagined. These aren't just technical questions. They are stories written in the chemistry of motion. Every molecule on 3i Atlas carries a fragment of that story. And so we watched, and measured, and wondered. When two objects pass through your cosmic neighbourhood, each from a different origin, each bearing different features, it's only natural to start comparing them. Oumuamua and 3i Atlas, both labelled interstellar, both observed from Earth in the span of just a few years, were not just isolated anomalies anymore. They were the beginning of something that could one day become a field of study all its own, interstellar object science. And so, comparisons began, gentle ones, scientific ones, not to declare a winner, but to sketch a contrast. Oumuamua had been enigmatic, no visible tail, no clear outgassing, a strange, rapid rotation. An acceleration that couldn't be fully explained by gravity alone. It left behind more questions than answers, and for many it marked the beginning of a new curiosity about the space between stars. 3i Atlas, by contrast, was quieter in its mystery. It played more by the rules we understood. It outgassed faintly. It showed a soft coma. Its light curve was smoother, its rotation gentler. The pieces fit more easily into our models, but it still brought its own puzzle pieces. The fact that it was detectable for months made all the difference. Observatories around the world, both on Earth and in orbit, had time to observe it. Space telescopes like Hubble and instruments from ground-based observatories could coordinate. For once, we weren't reacting after the fact. We were tracking in real time. From this patient observation, we learned that 3i Atlas moved along a shallower hyperbolic path than Oumuamua, meaning it wasn't travelling quite as quickly, and its approach was less steep, allowing more days of favourable positioning for telescopic study. All of that added up to more data, and in the data were hints, whispers really, about where these objects might fit into the broader structure of our galaxy. Because interstellar objects are more than just visitors. They're clues. Their trajectories give us a sense of the velocity distributions of objects in the galactic disk. Their compositions give us small windows into distant planetary nurseries. Their light, their shape, their speed. It all feeds into a model of a dynamic galaxy, where matter moves endlessly, quietly, across space and time. Some theorists even began to suspect that our solar system might contain captured interstellar objects, small bodies that were caught long ago by the sun's gravity and now orbit quietly, pretending to be native. If true, it would mean that the distinction between ours and theirs might be blurrier than we thought. 3 Atlas revived these possibilities. It offered fresh momentum to an old idea, that planetary systems constantly exchange matter, that every system, every star, is connected to others not by beams of light, but by ancient rocks, cosmic castaways, drifting for millennia, occasionally brushing past new suns. In that light, 3i Atlas wasn't just a curiosity. It was a participant in a vast, slow conversation, a geological exchange across incomprehensible distances. Astronomers began running new simulations. How often do interstellar objects pass near Earth? What masses and velocities would make capture likely? What observational biases have kept us from noticing more? The results were humbling. Some models suggested that tens of thousands of interstellar objects could be within the solar system at any given time, most of them tiny, too faint to see, too quiet to track. But some might be visible, and if we look in the right way, we might just catch them. That means the next chapter of interstellar study may not rely solely on chance encounters. It may involve deliberate searches, cataloguing the thousands of near-Earth objects we already track, analysing their orbits, and asking which ones don't quite belong. This is the quiet revolution 3 Atlas helped to spark. Not through drama, not through spectacle, but through the steady revelation that we might already be surrounded by messengers from other stars, that these aren't once-in-a-century events, that interstellar drift is part of the rhythm of the galaxy, and it shifts the way we think about the space between stars, not as empty, but as filled with quiet wanderers, each one carrying its own slow story. Each one reminding us that even in the vastness of space things move, things change, things arrive unannounced, then fade, and all we have to do is notice. The term interstellar object sounds large, perhaps even imposing, but in reality most are likely small, silent travellers, cold, dim, untraceable until they pass very close. To earn the interstellar title, an object doesn't need to shine or shout. It simply needs to move in a way that cannot be explained by the sun's pull alone. That's the heart of it. The orbit. Oumuamua and 3i Atlas both travelled on what's known as a hyperbolic trajectory. Unlike the elliptical paths of planets or the stretched loops of comets, a hyperbolic orbit isn't a loop at all. It's an open curve, one that approaches the sun just once before continuing outward forever, never to return. This motion tells us something fundamental. These objects were never part of our solar system. They didn't begin in the Kuiper Belt or the Oort cloud or any of the quiet, distant zones that hold ancient debris. They were formed elsewhere, ejected by forces we'll likely never witness, and sent drifting across the velvet black between stars. It's a strange thought, that these unassuming pieces of rock or ice may have spent millions or even billions of years in isolation, drifting, spinning, quietly orbiting the galactic centre alongside stars, nebulae and dark matter halos, all caught in the same slow cosmic dance. And then, by chance, their path curved just enough to bring them near our sun. In the case of 3i Atlas, the approach was graceful. It entered the inner solar system on a wide arc, passing near Earth's orbit but never coming dangerously close. There was no need for alarm, no cause for headlines. only quiet excitement among astronomers who recognized the significance of its trajectory. The angle of entry was steep enough to make it unmistakably foreign, but not so steep that we couldn't follow it. And that balance made it special, because to see a hyperbolic orbit is to witness a story in motion, one that began elsewhere and won't end here. To detect such an object, telescopes track its position night after night, calculating how much it shifts against the starry background. They use this motion to map its path through space, then compare that path to the pull of the sun. If the curve is too open, too wide to be caused by gravity alone, it earns that interstellar label. But there's a subtlety. Some objects have near hyperbolic paths just on the edge. Many long-period comets appear to have open trajectories, but that's often due to measurement error or gravitational nudges from planets. True interstellar objects, ones that come in fast and exit even faster, are much rarer. That's why Oumuamua was such a shock. It wasn't just that it moved quickly, it was that no known gravitational interaction could explain its speed and direction. It came from the void, and it returned to it. 3i Atlas followed suit. Its orbit, once calculated, placed it firmly in interstellar territory. It wasn't bound to our sun, it was a visitor. But it also stayed long enough for us to ask better questions. Why do these objects travel as they do? What does their velocity tell us about their past? If they're ejected from forming star systems, how far do they go before something curves their path again? The answer lies in galactic motion. Our solar system orbits the centre of the Milky Way once every 250 million years. As we drift through this cosmic carousel, we occasionally pass near other stars, or through denser regions of dust and gas. And just as our sun can eject comets into interstellar space, so too can other stars. Imagine the galaxy as a vast ocean. Every star system tosses a few pebbles outward, every few million years. Most go unnoticed, but once in a great while, one of those pebbles skims across the surface near us, and if our instruments are sharp enough, we catch it in flight. That's what happened with 3i Atlas. Its velocity and path suggest it was ejected long ago. Not in our lifetimes. Not in the lifetimes of our species. Perhaps not even in the era of Earth's first trees. It may have begun its journey when the dinosaurs still ruled this planet, or before Earth had any land at all. And it has been drifting ever since. No engine, no course correction, just gravity, just motion, just silence. Now, as it exits our solar system, its speed will carry it outward, past Neptune's orbit, into the heliopause and beyond, into true interstellar space once again. And unless it meets another force, another star, another gravitational embrace, it will drift forever. That is the nature of a hyperbolic path. It is a farewell. And yet, for a brief time we shared space with it. We saw it with our instruments. We traced its motion against the stars. We wondered where it had been and where it would go next. That's the quiet gift of interstellar objects. Not just what they are, but what they represent. They remind us that our solar system is not a sealed box. It is a part of a wider flow, a drift, a hush across the sky, filled with things we cannot predict but can learn to recognize. And as our instruments improve, so too will our ability to catch these silent travelers, not just after they've passed, but maybe before. If interstellar objects like 3i Atlas and Oumuamua teach us anything, it's that the space between stars, the interstellar medium, is not empty. It is sparse, yes, so thin that a single atom may occupy a cubic centimetre. But it is not a void. It's a medium, a subtle, drifting sea of dust, gas, and long-forgotten fragments. And any object that spends millions of years wandering through it carries the imprint of that sea. 3i Atlas entered our solar system with a quiet story already written on its surface. A story etched not by gravity or impact, but by patience, by slow interactions with that invisible material between stars. The interstellar medium is made up of hydrogen, helium, trace elements, and dust. Over long periods, it can strip or alter the outer layers of objects like Thruel's atlas. Cosmic rays bombard them constantly. Microscopic collisions wear down edges. Cold temperatures preserve volatile ices, but also make their surfaces brittle. And over millions of years, this slow exposure creates what some astronomers call a cosmic patina, a kind of interstellar weathering, a dulling, a layering of chemistry that's unique to objects from beyond. Studying that patina is like reading a logbook written in starlight. Spectroscopy, the study of how light reflects off an object, lets us decode some of this. When scientists looked closely at 3I Atlas, they found hints of ices and carbon compounds. Its spectrum had broad features similar to known comets, but not identical. There were small shifts, tiny deviations that suggested a different history of radiation, temperature, and time. One especially curious detail was the presence of carbon monoxide gas, more than we typically see in solar system comets. This could mean the object formed in an unusually cold environment, perhaps far from its parent star. Or it could mean it hadn't undergone as much heating or processing as comets that have looped around the Sun for millennia. In either case, it was different. It was also delicate. Unlike rocky asteroids that can survive repeated collisions and hard impacts, objects like 3I Atlas are fragile. Their icy interiors and porous structures make them vulnerable to crumbling under stress. That's one reason why capturing or even approaching an interstellar object up close is so challenging. They may not hold together if touched, yet they hold secrets, not just about themselves, but about the medium they've passed through. The interstellar medium is largely invisible to us, but it subtly shapes everything that drifts through it. A particle of dust here, a collision there, a slow shift in surface chemistry over 1 billion years. 3 Atlas didn't speak loudly about those experiences, but its surface hinted at them. Its composition carried the memory of passage. There's also something poetic in how such an object might taste the galaxy. A kind of cosmic wind shapes it over time. Not a breeze as we know it, but a faint pressure. A murmur of particles moving between stars. The same wind that carries radio signals. The same dust that feeds the birth of new solar systems. In this sense, 3I Atlas was not just from somewhere else, it was of somewhere else, and not just one place either. It may have passed through multiple regions of the galaxy, each one leaving a trace. Think of a seashell shaped by distant tides. The interstellar medium is vast and not all regions are alike. Some are denser, near stellar nurseries. Others are more rarefied. Some carry magnetic fields. Others, shock waves from past supernovae. Each pocket of space has its own fingerprint, its own influence on passing travellers. The idea that an object could carry all of that history, that it could arrive at our doorstep quietly shimmering with clues from across the galaxy, is both humbling and serene. Of course, much of this remains speculative. We can't track the full journey of 3I Atlas. We can only guess at the forces that shaped it. We rely on light, models, and silence. But those guesses, guided by patient observation, help us build a richer picture of the cosmos. And slowly, section by section, we're learning how to listen better. We're learning that each interstellar object is not just an arrival, but a sample, an offering from a different part of the galaxy. And even if we never touch them directly, their presence is a quiet map, a reminder that we are surrounded by stories much older and broader than our own. So when we say that 3I Atlas changed everything, we don't mean through spectacle or certainty. We mean through context, through accumulation, through the way it gently shifted our sense of what's possible. It told us, in no uncertain terms, that the silence between stars is not just silence, it is motion, it is matter, it is memory. And every once in a while, one of those memories drifts close enough for us to see. It's easy to imagine that a visitor like Three-Eye Atlas simply appeared one day, gliding into view with calm intent, but the reality is more subtle. Long before it became visible in our skies, it was already on its way, approaching quietly, unnoticed, along a path set in motion perhaps hundreds of millions of years ago. How it entered matters, and how close we came to missing it, again reminds us how fragile these encounters can be. Three-Eye Atlas approached from a direction slightly off the ecliptic, the plane along which most planets orbit. This made it harder to detect. Most sky surveys, even today, concentrate along the ecliptic, where solar system activity is highest. That makes sense if you're tracking asteroids or comets, but not if you're looking for rare visitors arriving from deep space. Its velocity was also part of the puzzle. It wasn't fast enough to stand out immediately, nor was it slow enough to suggest a bound orbit. It sat right in the middle, an ambiguous motion that required careful observation over several days before its true nature became clear. The object didn't blink like a flare, didn't shimmer with cometary brilliance. It moved with restraint. And yet, even that quiet motion told us something precious. It had not been captured by the sun. That's one of the key signs of interstellar origin. Most comets that orbit the sun have elliptical orbits, long stretched loops that carry them far away before they return. But interstellar objects don't loop. Their paths are open. They sweep in, curve gently, and continue outward, a hyperbolic goodbye. But here's where things grow more delicate. Not all hyperbolic orbits mean interstellar origin. Some solar system comets can be nudged into hyperbolic paths through interactions with planets, especially Jupiter. This gravitational assist can fling objects outward on escape trajectories, mimicking the paths of true interstellar visitors. So how do we know? We look at their incoming velocity, their speed relative to the sun, before any interaction. If that speed is too high to be explained by gravitational nudges, then the object must have originated from beyond the solar system. Three-Eye Atlas met that threshold. Its inbound velocity was well above solar escape speed, even before the sun began to pull. That's how we knew. This object didn't belong to us. It never had. Its approach trajectory was another clue. It came from a region of sky not associated with the common origins of solar system comets. Its motion couldn't be matched to any known debris family. It was simply different, and that difference almost hid it from us. Despite our growing network of sky surveys, we still miss many objects like this. The sky is vast, and most interstellar visitors are small, dark, and fast. Catching them requires just the right alignment of telescope coverage, weather conditions, and timing. Atlas was lucky, but luck favours the prepared. Because of improved algorithms and quicker data processing, the system flagged Three-Eye Atlas early enough to mobilise global follow-up. Within days of discovery, observatories worldwide had turned their attention to it, and for weeks they continued to observe it, collecting more data than we ever managed with Oumuamua. That allowed us to track its path more precisely, to understand its orbit with less uncertainty, and to tease out faint details in its light. In a sense, the object entered our awareness long after it had entered our space. It had already passed through the outer solar system, already begun its slow turn around the sun. We simply hadn't seen it yet. This gap between reality and recognition is a quiet reminder of how much we still miss. For every Three-Eye Atlas we detect, how many slip by unnoticed? How many move in from odd angles, too faint to register, too fast to track? How many are smaller or darker or shrouded in dust? Astronomers estimate that thousands of interstellar objects may pass through the solar system every year. Most are undetectable. A handful might be large enough to observe if we happen to be looking at the right patch of sky at the right moment. And that's the beauty of this new era. We are getting better at looking. Telescopes like the upcoming Vera C. Rubin Observatory will give us wider, deeper surveys, we'll detect more faint movers, we'll follow up faster, we might even catch objects before they reach their closest approach, something we've never done before. That could change everything. If we see an interstellar object early enough, we might launch a small spacecraft to intercept it. We might collect data from closer range. Maybe one day, even gather dust samples or test its composition with onboard instruments. But that begins with understanding how they arrive and how easily they could be missed. 3i Atlas entered quietly, but we saw it, and from that simple act of seeing, we learned so much, not just about this one object, but about the architecture of our detection systems, about the holes in our coverage, about where to look next time. It was a lesson in patience, in preparedness, in humility. Because even with our best tools, the universe often moves just beyond the edge of our awareness, and it's only by slowing down, by watching carefully, that we catch the rarest things, like 3i Atlas, arriving silently from the cold dark, not demanding attention, just passing through. If Oumuamua startled us into awareness, and 3i Atlas deepened that awareness, then the question naturally becomes, how many others are there? It's a question without urgency, but with profound implications. Because once you see 2 visitors from outside your system in a short span of time, you begin to wonder whether they were ever rare at all, or whether we had simply not learned how to listen. The idea that interstellar objects might be common isn't new, but it has taken on fresh energy in recent years. What once seemed like a cosmic coincidence now feels like a gentle pattern, a quiet rain of fragments drifting across our path. Some models suggest that for every star in the Milky Way, there may be hundreds of millions of ejected planetesimals, small bodies flung into the dark during the chaotic years of solar system formation. These fragments, unbound and unsheltered, would travel the galaxy indefinitely, crossing paths with other systems, brushing near distant stars, or sliding through unnoticed. If even a fraction of them passed through our solar system, that would mean a steady stream of interstellar visitors, tiny and faint perhaps, but real, and most would go undetected. They would arrive without warning, too small to reflect much sunlight, too fast to track easily, too brief in their appearance for our current networks to catch. But as our detection systems grow more sensitive, we are beginning to see the first edge of that stream. Each object we find adds weight to the idea that interstellar drift is not a rare event, but a quiet background process, part of the galaxy's natural breath, as common as starlight if you know where to look. The idea is humbling. It suggests that the solar system is not isolated, not a self-contained bubble. It's a port along a route that spans across time and space, and while most traffic slips past in silence, every so often, we catch a glimpse. We can begin to estimate how many we might see in the future. With instruments like the Vera C. Rubin Observatory, researchers predict that dozens of interstellar objects may be detected each year, if not more. Most of these will likely be small, perhaps the size of a car or a building, too small for missions but not too small to observe, not too small to track, and with each new detection, we will gain a broader sample, more diversity, more understanding. Some may behave like Oumuamua, dry, fast and enigmatic. Others may glow like 3i Atlas, active, icy and comet-like. A few may be unlike anything we've seen. Some may spin rapidly. Others may tumble slowly. Some may carry strange chemistry. Others may seem oddly familiar. And every one will be a fragment of somewhere else. A page torn from a book we've never read. A whisper from a distant solar system. They may come from places with multiple suns, or from systems orbiting quiet red dwarfs, or from the dusty outskirts of worlds that never formed planets at all. And in each of them, we'll see more than data. We'll see the motion of the galaxy itself. Because these objects are not just wanderers, they're evidence of dynamism, of gravity doing its quiet work across billions of years, of collisions, close encounters, and ejections. of solar systems shaping one another not through light, but through stone and ice. It's possible, too, that some of these objects may have passed through multiple star systems over the course of their lifetimes, swept gently in and out by gravity, altered slightly by each pass, carrying with them a cumulative memory of cosmic neighbourhoods. If that's true, then they're more than visitors, they're messengers. Not in the metaphorical sense, but in the geological one. They carry minerals and molecules that tell stories, the ratios of isotopes, the presence of frozen gases. The trace fingerprints of magnetic fields or radiation damage. These things whisper histories we cannot otherwise access. They bring news of other suns, and that, softly, gently, reshapes how we see ourselves. It means the boundary of our solar system is not fixed. It is porous, it breathes, it exchanges. And the more we pay attention, the more we see that we're not on an island but in a current. The current is slow, unhurried, like the motion of 3-eye Atlas across our skies, but it is steady, it is ongoing, it is cosmic in scale, and it connects us to everything else. One of the most quietly profound shifts brought about by 3-eye Atlas is the way we think about origin. Not just where a single object began its journey, but how objects like it might be born, shaped, and ultimately set adrift into the space between stars. Theories abound, and like all good scientific questions, the answers remain open. Some suggest interstellar objects are the leftover debris from early planetary formation. When a new star system forms, it doesn't do so with tidiness. Gravity pulls dust into clumps, clumps into rocks, rocks into planetesimals, and some into planets, but not all material finds a home. Some remains in the outskirts, stirred, scattered, unsettled. When large planets form, especially giants like Jupiter, they can fling nearby objects away with incredible force. If the timing and angle are right, those objects might escape the pull of their own star entirely, sent into the galaxy to wander. It's likely that this is how 3-eye Atlas began. As part of the early detritus of a star system, cast off into the dark not by design, but by gravitational accident. But there are other theories too. Some interstellar objects might come from violent collisions, two protoplanets crashing into one another, scattering molten fragments into the void. Others might be torn from distant belts of icy bodies by the slow nudges of passing stars. Some might even be remnants of moons, ejected by chaotic planetary reshuffling. And more speculative still, some may be fragments of ancient objects destroyed near black holes, crushed, sheared, accelerated, survivors of environments we can only model in theory. 3-eye Atlas doesn't carry a label that tells us its past, but it does carry hints. Its composition, its reflectivity, its shape, all speak softly of origin. The carbon monoxide detected in its coma, for instance, may suggest it formed far from any star. A cold place, a quiet place, maybe a region like the outer Oort cloud in our own system, a halo of icy bodies loosely held in the sun's embrace, or perhaps even farther. Its structure, likely porous, fragile, could mean it was never warmed significantly, never reshaped by a nearby star, never part of a planet that underwent internal melting or chemical differentiation. In that sense, 3-eye Atlas may be almost primordial, unmelted, unaltered, a piece of raw galactic material. These qualities make it precious, not because of what it is, but because of what it hasn't become. It has not been processed into a world. It has not been burned by repeated passages near a sun. It has not been shattered and reassembled by impact. It is quiet, preserved, and that means its chemistry is old, perhaps older than Earth, perhaps older than the sun, perhaps formed in a dust cloud that drifted through space while the Milky Way still shimmered with newness. To hold something like that, even with our instruments, is to reach into deep time. It invites a soft kind of awe, the kind that doesn't flash with revelation but builds slowly, quietly, like starlight across years. And here's something else to consider. If 3i Atlas came from another solar system, and we believe it did, then it means other stars too have rocky debris fields, have collisions, have formations and ejections, have motions like our own. This reinforces a simple but profound idea, that we are not unusual, that our solar system is not the exception, that we are one of many star systems flinging fragments into the dark, some of which, very rarely, intersect with each other, and that somewhere, out there, a different star's astronomers may be watching an object from our system drift past their own sun, blinking softly in alien skies. Because exchange is inevitable in a galaxy like ours, given time, and we've had plenty of it, these small visitors become common, not to the eye, but to the story, to the structure of things. The Milky Way is more than stars and gas. It is a cradle of interactions, and every visitor like 3i Atlas reminds us of that. These aren't rogue bodies, they are letters, still sealed. So where might 3i Atlas have been before it arrived? We can't say exactly. The galaxy's too vast, its gravitational tugs too subtle and overlapping over the timescales we're discussing. But we can trace the general direction it came from, and ask gentle questions about what kind of journey might have delivered it here. Its inbound trajectory pointed loosely toward the Carina Vela region of the southern sky, a patch rich with young stars, gas clouds, and stellar nurseries. Not a precise origin, not a known system we can name, but a direction, like a breeze that carries a leaf from somewhere in a forest. There's a good chance 3i Atlas has spent millions of years drifting in the galactic outskirts, perhaps tens of millions, perhaps more. Maybe it passed through the Milky Way's thin disk, the region where most stars and planets live. Or maybe it lingered in the galactic halo, that quiet spherical cloud of dark matter and scattered objects that envelops our entire galaxy like a soft shell. The halo is a place of deep time. It is sparse, dark, and largely invisible to us. And yet, it's filled with ancient stars, some of the oldest in the galaxy. It's not hard to imagine that 3i Atlas could have spent a vast stretch of its life there, orbiting the galactic centre on a long looping path before its trajectory shifted just enough to bring it near our sun. What caused the shift? Perhaps a nearby star passed close, just close enough to nudge it. Or maybe it drifted into the edge of a molecular cloud, where gravity is uneven and small objects can be deflected like pebbles in a river bend. Or perhaps the drift was always there, slow, certain, unhindered. Once an object is unbound from its home system, it becomes a citizen of the galaxy. It is no longer shaped by the warm pull of a familiar sun, but by the slow geometry of the Milky Way itself. This means that its origin is both singular and plural. It may have formed in one place, but its path since then has crossed through many invisible territories, and like a message passed hand to hand, it carries more than just its beginning. It carries its whole journey. That journey may have included passes near other star systems, even brief encounters with planetary systems like ours. Each time, gravity would have tugged slightly, bending its course, accelerating or decelerating it in small ways. Over millennia, these changes add up. This is how the Milky Way moves, slowly, softly, but with purpose. And in this context, 3 Atlas is a kind of time capsule from the galactic flow. It's possible that, at some distant point, it passed close to another planetary system, close enough to feel a gravitational nudge, maybe even close enough to observe a distant sun. If we were to imagine standing on such a body, it might have been a dark, frozen world. No atmosphere, no sound. Just a slow rotation under starlight, each sky filled with unfamiliar constellations. It might have known silence more completely than we ever could. Then one day that silence would have broken, faintly, as the object passed near our sun. the ice on its surface warming ever so slightly. Molecules vibrating in response, a soft release of vapour, a coma forming, a tail unfurling like a sigh, and we, here on Earth, noticing that brief shimmer. That shimmer told us, this one is not from here. And the shimmer was fleeting, because now 3i Atlas is on its outbound path, its journey through our system nearly over. It's headed back into the halo or beyond, on a new trajectory shaped by its brief solar encounter. This is part of the beauty of interstellar dynamics. These visitors don't simply enter and exit in clean, mirrored lines. The sun's pull bends their path, shifts their velocity, sometimes even steals energy from their motion. Each pass changes them just a little. 3 Atlas will now follow a new hyperbolic path, different from the one it arrived on, slightly more curved, slightly faster, its course altered by sunlight, gravity, and the gentle push of its own outgassing, and that new path will take it away from us forever. But its legacy remains in data, in models, in the growing awareness that these objects are part of a larger galactic exchange. Because for all its mystery, 3i Atlas gave us something we hadn't had before. Time. Time to look. Time to listen. Time to wonder. And perhaps above all, time to realise that space is not static but alive with motion. That across millions of years, tiny icy bodies carry their own starlit memories. That sometimes, just sometimes, they pass near enough to share them. As 3i Atlas faded into the darkness beyond the sun, it left behind more than data points. It left echoes. Not the kind that bounce off canyon walls, but the quiet intellectual kind. The kind that ripple through the scientific community, shifting long-held assumptions and awakening new lines of inquiry. Among the most curious of these echoes was a question many had tiptoed around since Oumuamua first passed by. Could some of these visitors be more than just rock and ice? Could any of them, however unlikely, be artificial? It's a question often spoken in whispers and always approached with caution, not because it's a silly idea, but because science thrives on humility, on restraint, on evidence. And so, the suggestion is rarely a claim. It's a possibility. A what if, floated like a balloon in the still air of astronomical thought. Oumuamua's strange acceleration without visible outgassing had nudged that balloon into view. Its cigar-like, or perhaps pancake-like, shape, combined with the lack of a visible tail, led some to speculate, what if it were a light sail? What if its acceleration came from radiation pressure? Most in the field lean toward natural explanations. Sublimation of invisible ices, rotation-induced forces, measurement error. Still, the oddness remained. 3i Atlas helped bring balance back into the conversation. It behaved more like what we expected from interstellar comets. A faint tail, detectable outgassing, a more familiar light curve. In a way, its presence reassured many astronomers, confirming that not every interstellar object was inexplicable, that there was a range of behaviour we could place within natural non-sensational bounds. But still, the debate didn't end. It simply deepened, because now we had contrast. We could see side by side two travellers, one familiar, one strange. And that allowed a more grounded question to emerge. How would we know? How would we truly distinguish a natural interstellar object from something engineered? This is not a question of alien civilizations in the cinematic sense. No glowing ships or blinking lights, but rather subtle structures, quiet artifacts, objects that drift like everything else, but with patterns that suggest intent. To begin answering, we must first understand what natural objects do. We study spin, light reflection, surface chemistry, trajectories, composition. From this, we build profiles, what ice-rich comets look like at certain distances, how light behaves across rough surfaces, how solar radiation affects rotation, These models give us the framework to detect anomalies, not by proving something is artificial, but by noticing when it doesn't fit the pattern. And that's where 3i Atlas becomes so important. It helps define the pattern. Its behaviour helps establish a baseline of what we might expect from a typical interstellar comet. Its spectrum, its speed, its path through the solar system, its fading tail. All of this forms a quiet comparison point, so the next time we see a visitor, perhaps one that again behaves strangely, we'll have more to compare it to. We'll be better equipped to ask without sensationalism whether the object is just rare or truly odd. This is not a hunt for aliens, it's a study of exceptions. It's science, not because it declares answers, but because it learns how to ask better questions, and those questions are becoming more refined. What kinds of trajectories are too perfect? What shapes spin in ways that rock shouldn't? What kinds of surfaces reflect light like metal, not mineral? All of these are questions we can ask now, not because we expect a dramatic answer, but because 3i Atlas showed us that some objects fit the mould, and when one doesn't, that absence becomes meaningful. It's not that we expect to find something artificial, but it's now within the scope of imagination. As long as it's treated gently, it can remain part of the conversation. Because when you realise that material from other star systems regularly drifts through your own, the line between us and out there begins to blur. And once that line blurs, the galaxy becomes smaller, not in size, but in separation. We are part of a broader system, a wider sky, a shared motion, and in that motion, not everything will be familiar. Some will be like 3i Atlas, soft-spoken, comet-like, behaving as nature often does. Others may be like Oumuamua, slender, silent, quick, leaving us with more questions than answers. Both teach us something, both belong here, both expand our idea of what it means to watch the sky. As we follow 3i Atlas on its retreat from the inner solar system, we're reminded that these brief encounters are precious because they are fleeting. Once an object curves around the sun and begins its outbound arc, it dims rapidly. It slips beyond the reach of our instruments. It fades, not just from sight, but from the realm of active study. And yet its influence lingers. Every observation made while 3i Atlas was still visible became a reference point, a data set, a quiet thread in the growing tapestry of interstellar science. But even more than that, it became part of a shift in our thinking. These objects are not just anomalies. They are participants in something larger. For decades, we've studied the solar system as a closed set. Planets, moons, comets, asteroids, all interacting within a relatively isolated gravitational dance, the sun at the centre, bound orbits as the rule. But 3i Atlas reminded us that this system is more porous than it seems. That material from beyond doesn't just exist, it occasionally arrives, drifts through, leaves clues, and perhaps, just perhaps, continues onward with a new trajectory, shaped ever so slightly by its encounter with us. This paints a different picture of the solar system, not as a sealed sphere, but as a slow exchange zone, a cosmic intersection, a place where paths cross, sometimes without touching, but never without consequence. 3 Atlas altered our perspective not just on objects but on space itself. It became easier to imagine the solar system not as a walled garden, but as a way station, a quiet node along a galactic web of motion, a place where fragments of faraway systems can pass, curve, and move on. And this invites another idea, perhaps the most poetic of all. What if these visitors are not rare at all? What if the solar system is constantly being brushed by foreign dust? What if tiny grains of other solar systems land on Earth every day, too small to notice but still in a way present? In fact, we now know this is likely. Micrometeorites of interstellar origin have been detected in Earth's atmosphere. Individual atoms, molecules, even tiny specks of mineral, that travelled unimaginable distances only to end their journey in our skies. 3i Atlas is just a larger version of that idea, a visible one, a story-sized one, and it raises the possibility of a deeper future, a future in which we do more than observe, a future in which we intercept. Right now, we only have the means to watch these objects from afar, but scientists have begun exploring the idea of missions that could one day catch up to an interstellar visitor. Small spacecraft with fast launch capabilities, ready to be deployed the moment a new object is detected. Such a mission would be difficult, timing would be tight, but the payoff would be immense. Imagine flying alongside something like 3i Atlas, watching it from just a few hundred kilometers away, scanning its surface, measuring its composition directly, perhaps even releasing a small impactor to stir dust for analysis. We'd learn not just what it's made of, but how its structure holds together. We'd see if its surface is smooth or fractured, if it spins in silence or wobbles like a cosmic leaf. That kind of encounter would be a first, a conversation, not just a glance. And each new object like 3i Atlas brings that dream a little closer, helps refine the detection, helps refine the timing, helps us prepare. Because the more we study these visitors, the more we realise they're part of something larger, a process, not an event, a system, not an exception. They are the driftwood of the galaxy, the windblown seeds of distant stars, and maybe, one day, we'll not only observe them, we'll greet them, with instruments ready, with questions prepared, with the quiet hope that in meeting them up close, we will come to understand not only their journey, but our own. Because if our solar system sends out its own fragments, if pieces of Pluto or comet dust or even Voyager probes one day drift near another star, then we too are part of the pattern. We're not only observers of interstellar motion, we are participants. What can we truly learn from these quiet travellers? The obvious answers are scientific: composition, structure, motion, trajectory. But beneath those surface facts lies something more expansive. Every interstellar object that passes through our solar system, even if only once, offers a chance to test the boundaries of what we believe we know about how star systems live, evolve, and share their stories. 3i Atlas, in particular, showed us the scientific value of preparation. Its long visibility and relatively slow speed allowed telescopes around the world to coordinate. Instruments across the electromagnetic spectrum were able to contribute. And from those shared efforts emerged a more complete picture, not just of this one object, but of what interstellar objects can be. One surprising insight was how well we could use its presence to test our models of planetary system evolution. In recent decades, astronomers have used computer simulations to model how planets form. These simulations often reveal the chaotic early stages, where massive bodies interact, scatter, and sometimes eject their neighbours. These ejected objects become interstellar nomads, no longer bound to any star. 3i Atlas could be one of these. Its structure suggests it never coalesced into a planet or moon. Its low density and icy composition hint at a quiet origin, perhaps a region analogous to our own Oort cloud, a place cold enough to preserve fragile ices, far enough from its star that gravity's grip could be broken by a passing giant or a stellar encounter. In studying it, we gain insight into those ejection processes, not just how often they happen, but what kinds of material get ejected. The fact that 3i Atlas appears so comet-like suggests that icy debris is more likely to be set adrift than rocky cores or iron-heavy fragments. This, in turn, tells us something about the outer regions of other systems. They may be filled with small, icy remnants waiting to be stirred loose, and when they are, they don't just disappear. They become part of the galaxy's quiet circulation, a slow, wandering network of materials travelling between stars. This realization has a deeper implication. We can study exoplanetary systems without ever leaving our own. Each interstellar object is a physical sample, a tangible artifact from a system we cannot otherwise reach. It's as if a tiny piece of another world flew to us, unannounced, and waited silently for us to notice. We already study distant solar systems using light, tracking exoplanets by their shadows or wobble. But these methods give us only broad outlines. Interstellar objects like 3i Atlas offer something different. Texture, chemistry, detail. We can analyse their spectra. We can compare their isotopic ratios to those found in solar system comets. We can ask, is their ice purer? Is their dust older? Do they contain organic precursors common across worlds? These are slow, careful questions. They don't shout, they unfold, and the more samples we have, the more confidently we can answer them. In time, we may find patterns, similar compositions across multiple interstellar objects that hint at common processes in planet formation, or striking anomalies that suggest exotic origins, perhaps even from systems very unlike our own. In this way, 3i Atlas becomes more than a curiosity. It becomes a test case, a gentle probe into the chemistry of the broader galaxy, and every new object detected after it builds on that story. Eventually we may be able to classify interstellar visitors into categories: cometary, asteroidal, metallic, organic rich, each type telling us something different about where it came from. And just as we now map exoplanets by their sizes and orbits, we may one day map the interstellar population by material and motion. But for that to happen, we need a broader foundation, more observations, more time and patience, because the next 3i Atlas could already be on its way. It might arrive next year, or a decade from now. It might be larger, brighter, slower, or smaller and stranger still. We don't know yet, but what we do know is that we're ready in a way we weren't before. Our instruments are sharper, our minds more open, our attention more attuned to subtle motion, and thanks to 3i Atlas we know what to look for. We know what matters. Not the drama of an object's arrival, but the calm clarity it brings, the chance to study, to reflect, and to gently expand our understanding of the galaxy we drift within. Because learning doesn't always come in shouts. Sometimes it arrives like a faint shimmer under starlight and leaves like a whisper. There's something quietly poetic about the way 3i Atlas appeared, not from the plane of our familiar solar system, but from a higher angle, off-axis, entering from a region of sky we rarely prioritize. It was a reminder that the cosmos doesn't arrange itself for our convenience. Its visitors do not follow the paths we map or expect. This realization has sparked a shift in how astronomers approach skywatching. For generations, much of our observational infrastructure has focused along the ecliptic, the flat plane where Earth and its neighbouring planets orbit. That focus makes sense. Most comets, asteroids, and near-Earth objects come from there. The gravitational ballet of our solar system plays out in that thin, disc-like stage. But 3i Atlas, like Oumuamua before it, didn't follow that script. Its approach angle was steep. Its path through the solar system sliced across the ecliptic rather than staying near it. And if our surveys had been any narrower, we might have missed it entirely. That realization has led to a gentle but important change. Astronomers are now looking up and out more often, not just along the usual lines, but into the quiet corners of the sky, the high latitudes, the poles, the places where unusual motion might whisper instead of shout. These regions, long treated as peripheral, are now seen with new significance. They may be where the rarest objects appear, those that don't belong, those that drift in from elsewhere. And the tools we use are changing too. Traditional telescopes take deep, narrow images, excellent for studying distant galaxies or faint stars, but less suited for catching fast-moving, transient objects. That's where wide-field surveys come in. Atlas is one such survey, scanning the entire visible sky several times each night. Others, like Pan-STARRS and Zwicky, Transient Facility, have joined the effort, and soon the Vera C. Rubin Observatory will dramatically expand our reach, photographing the sky with such frequency and depth that even the faintest motion may be revealed. This shift toward wider, deeper, faster coverage is transforming our ability to detect the unexpected. It means we're no longer just scanning for what we know is out there, we're opening ourselves to what we don't. And that brings with it a new kind of patience, because even though the galaxy is filled with motion, most of that motion is slow. Interstellar objects are fast relative to our Sun. Yes, but the time between discoveries remains measured in years, not weeks. There's no flood, no fire hose of new interstellar visitors, just a slow drift, a possibility on the horizon, a waiting game. But it's in that waiting that our observational discipline strengthens. We refine how we process data. We learn how to distinguish a true hyperbolic path from a false alarm. We tune our systems to notice smaller, fainter objects, ones that might have slipped past our awareness before, and over time we begin to fill in a new map, a sky not just defined by stars and galaxies but by motion, by the brief tracks of things that move differently, that come and go. 3i Atlas traced one such line, a soft curve across our celestial charts, and in doing so it reminded us that direction matters. Its origin point may never be fully known, but its angle, its arrival vector, told us that we cannot afford to stare only along the path of least resistance. We must look where we least expect, because that's often where the new stories begin, and there's something else. The fact that 3i Atlas came from an unusual direction tells us something about the distribution of interstellar objects as a whole. They are not funneled, they are not clustered, they come from everywhere. This makes sense when you remember that they are unbound. They are not tracing elliptical orbits around the galaxy. They are drifting freely, shaped only by the occasional gravitational nudge. Over time, their paths spread out, some climbing high above the galactic plane, others slipping below, all following the quiet geometry of mass and motion. And so, when we say that 3i Atlas changed everything, part of what we mean is this: it reminded us to widen our gaze, to think in 3 dimensions, to recognize that the sky is not a flat stage but a layered space, a sphere of possibility. A realm where motion may come from any direction, and often does. In the decades ahead, as our instruments continue to improve, we'll likely discover more objects like 3i Atlas. Some will be bright, others barely detectable. Some might follow familiar paths, others will surprise us entirely. But with each one, we'll refine our sense of orientation, not just in space, but in time. We'll begin to understand how interstellar material moves, how it spreads, how it drifts, and eventually we may come to see the entire galaxy as a system of slow exchange, a whispering network of stone, ice, dust, and time. We often speak of these objects, Oumuamua, 3i Atlas, as visitors, but perhaps the more honest term is passers-by. They don't stop, they don't orbit, they don't stay. They cross a threshold, curve slightly in the warmth of our star and continue on. Still, there's something haunting about that motion, because if 2 have come so recently, and if more are likely to follow, then perhaps even now, this very moment, another interstellar traveller is making its silent approach, unseen, unlit, on a trajectory that will bring it into our skies in a matter of months or maybe years. We wouldn't know it yet, not until it was close. Not until the data whispered something strange, a speed too high, a curve too wide, a motion against the background stars that just doesn't fit the familiar, but it might already be on its way. This possibility is not dramatic. It's calming in its way. It turns the sky into a quiet stage, always in motion, always ready for a new appearance. And what would it look like? Perhaps something smaller than Oumuamua, a rocky shard, no longer than a city bus, tumbling end over end through the night. Perhaps it has no tail, no glow, just a slow flicker of reflected sunlight as it spins. Or maybe it's larger, brighter. Perhaps it outgasses like 3i Atlas, releasing frozen breath as it warms. A short tail forms, then fades, a gentle halo, a brief visible signature on our telescopic plates. Perhaps it's stranger still. Perhaps its rotation is chaotic, unpredictable. Or its light curve wavers in ways we don't expect. Perhaps its composition, measured in those early spectroscopic glances, doesn't match anything we've catalogued. These are not hopes or dreams, just possibilities. Because now we know, the galaxy is not quiet. It is filled with slow motion, with fragments from other places, with pieces of other histories, and with each new detection, we ask ourselves, how soon could we know? This is where technology plays a quiet but crucial role. In the past, we spotted Oumuamua only after it had passed perihelion, its closest approach to the sun. We saw its tail lights, not its face. 3i Atlas was better. We detected it while it was inbound, giving us time to organise, to watch, to prepare. But the next one? Perhaps we'll see it before it even enters the inner solar system. With better sky coverage, faster data processing and predictive orbital modelling, we could one day spot these travellers before they arrive. Not by days, but by weeks, maybe even months. Imagine the change that would bring. Suddenly, we'd have time to observe, time to coordinate, perhaps even time to act. Small probes could be launched, telescopes repositioned, resources allocated to a specific patch of sky, not in hindsight, but in anticipation. This would represent a gentle shift, from reactive astronomy to proactive encounter. The future of interstellar object study may not lie in serendipity, but in preparedness. Because these visitors don't need to be rare to be remarkable. Even the most unassuming fragment carries the possibility of deep knowledge. Even the smallest icy pebble might hold molecules formed under a different star. So, we wait. Not impatiently, not anxiously. We wait the way astronomers have always waited, with open eyes, quiet instruments, and a readiness to listen. Because somewhere out there, right now, another object may be crossing the vastness, moving silently through the outer reaches of the solar system, unaware of our tiny presence, yet soon to be noticed. And when it comes, we will see it not as a mystery to solve, but a story to read. A long starlit sentence drifting across our sky. If one day we could catch an interstellar object, really catch it, what might we learn? It's a dream that hovers gently in the minds of scientists and space mission planners alike. The idea that, rather than watching these visitors pass us by, we might one day greet one directly, approach it, orbit it, perhaps even land softly upon it. This possibility, once the domain of science fiction, has quietly entered the realm of engineering discussions. Missions have been proposed, concepts have been sketched. Space agencies, both governmental and private, are starting to ask, what if we were ready next time? Because readiness is the key. Interstellar objects arrive unannounced. They move fast. They don't loop around for second chances. Any spacecraft meant to intercept one must launch quickly, accelerate rapidly, and travel with incredible precision. The technical challenges are immense, but not impossible. One concept developed in recent years is called Project Lyra. It explores the feasibility of chasing an interstellar object like Oumuamua with high-speed propulsion systems, ion engines, solar sails, or gravity assists. Another proposal imagines placing fast-launch probes in orbit, ready to deploy at a moment's notice when the next target is detected. It would be the celestial equivalent of catching a feather in the wind with a paper airplane, fragile, fast, and fleeting. And yet, the rewards could be profound. To examine an interstellar object up close is to see a material story older than Earth, a surface sculpted by time and space beyond our solar system. A record of dust, ice, and radiation gathered not from one sun, but from the dark roads between many. We might learn about the chemistry of alien clouds, the mineralogy of foreign debris disks, the stability of ices that have never felt our sun until now. We might find similarities that suggest planetary formation follows universal rhythms, or we might find differences, striking ones, that expand our understanding of how strange and diverse the galaxy's children truly are. There's another quiet possibility too. If one day we were able to bring back a fragment, just a sliver of such an object, it could change planetary science forever. We would hold, in our hands, a physical piece of a star system we've never seen. Not through a telescope, but through texture, through weight, through composition, and through that single fragment, we deepen our connection to the wider cosmos. Because every visitor like Three-Eye Atlas reminds us the galaxy is not still, it is filled with motion, with messengers, with moments of intersection, and we are not just passive observers, we are part of the exchange. Our own system sends material outward. Comets, dust, spacecraft. Somewhere, deep in the interstellar dark, a Voyager probe still drifts outward, carrying golden disks and greetings for no one in particular, a whisper from our corner of the sky. So perhaps one day another system will catch one of our fragments. Perhaps long after our lights have dimmed, something we launched will glide silently past another world. And there, it might be noticed, measured, wondered about. And in that wondering, another civilization might feel what we feel now. Awe, humility, the quiet thrill of catching something from beyond. This is the deeper purpose behind our fascination with interstellar objects. Not just scientific data, but a kind of communion. A recognition that we are part of something larger, that even in the stillness of space stories move, and sometimes they pass close enough to hear. We may never capture one, or we may catch many. Either way, we now know that we live not in isolation, but in motion, that the solar system is open, that our skies are visited, that we are not alone in drifting, but part of the grand galactic tide, and for now, that's more than enough. Now that our journey draws to a close, let's ease back from the far edges of interstellar motion. We've wandered together through the silent arcs of two strange visitors, Oumuamua, with its whispered mysteries, and Three-Eye Atlas, with its slower, softer revelations. We've traced their paths from the distant dark, through our sunlit skies, and back out into the star-strewn quiet. And through them, we've come to see the galaxy not as a void, but as a gentle swirl of motion, a place where matter drifts, sometimes aimlessly, sometimes with purpose, but always with story. We've learned that even a speck of ice or dust can carry with it the memory of a world long gone, or perhaps one that never truly formed. Tonight, as you settle in, perhaps you can imagine one of these objects gliding silently across the deep velvet sky above your rooftop. No trail, no flare, just the faintest motion, invisible to the eye but present nonetheless. A quiet traveller passing through the solar system, just as we drift through sleep. Let your breath slow. Let your thoughts fade outward, like starlight slipping between galaxies. There is no rush, no urgency, only the quiet curve of motion through time. And as you rest, remember, the space between stars is not empty. It is full of gentle intersections, of ancient light, of quiet stories waiting to be seen. Perhaps the next one is already on its way, but for now, let go of the sky, let your thoughts settle like dust on a comet's surface, and drift.